Hello and welcome to tutorial number 5. Our topic today is writing chemical formulas for ionic compounds, and this happens to be one of my favorite topics to cover in an introductory chemistry class, so I'm a little excited about that. All right, just a quick reminder before we get started. All of the tutorial notes are available from my website online, and I do recommend that you have those in front of you as you go through these videos. And with that said, let's begin. Okay, so we already know that for every element, the symbol and the name is going to be given in the periodic table. Okay, so let's write that up here. For elements, all of the symbols and the names are given in the periodic table. And you will sometimes run into a periodic table that doesn't have the full name written out, but for reference, if you're doing your homework and such, you're probably going to choose a periodic table that has both the names and the symbols written out for you. All right, we also know that atoms can lose or gain electrons in their chemical reactions. Okay, so let's first talk about what happens when an atom loses electrons. Well, when an atom loses electrons, its number of protons or positively charged particles will stay the same, but the number of negatively charged particles will decrease, leaving the atom with an overall positive charge. And we learned before that atoms with a positive charge are called cations. And typically cations will form from metals losing their valence electrons. Okay, so I'm going to write that here. Cations typically form when metals lose their electrons, resulting in an overall positive charge. So I'm just going to write a plus charge here. Okay. So remember, the number of protons is going to be greater now than the number of electrons. Positively charged particle, cation. And we refer to this process, the loss of electrons, as oxidation. I'm going to write that here as well. So let's put a little hyphen here. Oxidation. So when a metal loses its electrons, you might hear someone say that it has been oxidized. You might hear the charge that it obtains referred to as its oxidation state. This process is known as oxidation. Okay. And typically your metals are going to lose all of their valence electrons. And the goal is to lose all of the electrons in the outermost energy level, the valence electrons, so as to simulate the stable electron configuration of the most recent or preceding noble gas. And remember that your noble gases have octets, so really the goal is to achieve octet, okay? So that's what all these metals are trying to do, lose all their valence electrons and achieve octet. So let's write that here. So lose all valence electrons and therefore achieve, just write a little arrow here, octet. That stable electron configuration of a noble gas. Okay. All right, so it's really easy to figure out how many electrons a metal is going to lose, because you just have to be able to figure out how many valence electrons the metal has. It's going to lose, in most situations, it's going to lose all of its valence electrons. And the good news is that the number of valence electrons is always equal to the group number. So just look at the group number. The group number is equal to the number of valence electrons for the atom. I'll just write E for electrons. And therefore, that's going to be equal to the number of electrons lost. Okay. So let's take a look at the periodic table. If you happen to have one handy, you can go ahead and look at it. I'll just put one up here on the board so I can refer to it as I go along. Okay, so that means that all of your alkali metals, the metals in group 1A, they all have just one valence electron. And so you can expect them all, lithium, sodium, potassium, etc., you can expect them to always lose one electron and therefore obtain a 1 plus charge. Their oxidation state is 1 plus. So I'm going to write an example here. I'll just write the example for sodium. When it has lost 1 electron, we're going to write a plus. You don't actually write the number 1, you just write a plus for a 1 plus. Okay? So all of your group 2 alkaline earth metals, they have 2 valence electrons, and therefore they're going to lose those 2 valence electrons and obtain a 2 plus charge. Okay, so example, we'll just use calcium as our example. So when calcium loses its 2 valence electrons, it obtains a 2 plus charge, and we would indicate that like so. Okay. Group 3A, the elements in group 3A, remember we're just focusing on the main group elements here. Okay. So in group 3A, the metals all have 3 valence electrons, and so they lose all 3 to obtain a 3 plus charge. So for an example, let's use aluminum. So metal in group 3A, aluminum with a 3 plus charge. Okay. Group 4A, a little bit trickier. Okay. Group 4A here, we've got tin and lead. Now these 2 metals in group 4A, 4 electrons is an awful lot of electrons to lose. It takes energy to remove an electron from an atom. So removing 1 electron takes energy, removing 2 electrons takes more energy, removing 3 takes even more, and so it takes even more energy to remove 4 electrons. And so your group 4 metals won't always react by losing all 4 of their valence electrons. Sometimes they will lose only 2 and obtain a 2 plus charge, and sometimes they'll obtain a 4 plus charge. So we would say that your group 4 metals, tin and lead, have multiple oxidation states. So for example, you might run into tin with a 2 plus charge, and in another example with a 4 plus charge. Same thing for lead. Okay, so that's really all we'll say about elements with multiple oxidation states. That's really not going to be the focus in an introductory chemistry class. So I won't really be showing these multiple oxidation states again. All right? Okay. So let's go ahead and erase all this, and we're going to talk about one more thing pertaining to cations before we move on, and that is how to name them. And I'll just erase a little bit here. I'll add this right here. Okay, so names of cations. So to name a cation, it's actually very simple. All you have to do is take the element name and then add the word ion. So the element name plus the word ion. So for Na+, don't just call it sodium, call it a sodium ion. Because the elemental form of sodium actually behaves very, very different than a sodium ion. Okay, so you do want to make sure that you tack on that word and distinguish an ion from the neutral element, uncharged element. All right, let's go ahead and erase all this and go on to anions. All right, so anions form when nonmetals gain electrons to their valence shell. I'll just write E for electrons. And because electrons have a negative charge, you're gaining more negatively charged particles. Anions therefore have an overall negative charge. So I'm going to just do a little arrow negative charge. I'll circle it just to make it stand out. So anions will have a negative charge, more electrons than positively charged protons. All right, so we sometimes refer to the gain of electrons as reduction. Let's write a little hyphen there. Remember that the loss of electrons was oxidation. The gain of electrons is referred to as reduction. And your nonmetals will typically gain as many electrons as they need in order to fill up their valence shell and achieve the stable noble gas electron configuration of whatever noble gas it is that they're nearest to in the periodic table. So whatever noble gas follows them in the periodic table. So in other words, they're trying to achieve octet, that stable noble gas electron configuration where the outermost energy level is full with 8, octet. Okay, so let's write here, they will gain enough electrons to fill their valence shell. And achieve octet. Okay. All right, so let's go ahead and take a look at the periodic table again. So I'll go ahead and put that up here. Okay, so you can always tell how many valence electrons an atom has by looking again at the group number, for the main group elements anyway, looking at the group number. Okay, so if they want to achieve a total of 8, then what you'll need to do to figure out how many electrons a nonmetal is likely to gain is take the group number and subtract it by 8. That's going to tell you how many more electrons it needs to bring the total to 8, octet. Okay, so let's write that here. So take the group number and subtract it from 8. So 8 minus a group number will tell you the number of electrons gained by a particular atom. All right, so we're talking about nonmetals, so let's go ahead and start with group 4A here. Now group 4A, the only nonmetal there is carbon. And carbon actually tends to share electrons when it forms compounds, and therefore it forms molecular compounds, not ionic compounds. So I'm going to write here, carbon shares electrons. It forms molecular compounds, not ionic compounds. Okay, so we're going to skip on to group 5A. Carbon really won't apply here. All right, so group 5A, the nonmetals in group 5A, they have 5 valence electrons. So 8 minus 5, you can expect them to gain 3 electrons. I'm going to write 3 minus charge. You can expect them, let me write it down here, to obtain a 3 minus charge. Okay, so for an example, let's just use nitrogen here. You can expect nitrogen in an ionic compound to gain 3 electrons, and therefore you'll write it as a capital N with 3 minus charge. Okay. Group 6A, 8 minus 6. All of your group 6 nonmetals have 6 valence electrons, so they need to just gain 2 more. So that's not surprising then that they will obtain a 2 minus charge. So for an example, let's write oxygen. When it's gained 2 electrons, you'll write it as O with a 2 minus charge. Halogens, group 7A. They have 7 valence electrons. So 8 minus 7, they all need to gain 1 more electron to fill up their valence shell and achieve octet, that stable noble gas electron configuration. So they all obtain a 1 minus charge. As an example, let's write fluorine with a 1 minus charge. And again, you don't write the 1 here, you just write the minus, and it's assumed that it's a 1 minus then. Okay, last but not least, group 8A. Your noble gases, they are stable, they already have octet. Helium is an exception to that. Of course, it's filled up with only 2 electrons, but we still consider it as the octet, that stable noble gas electron configuration, a full valence shell. So not surprisingly, all of your noble gases you'll typically find in their elemental form, uncharged. The charge you can expect to be 0, okay? They don't typically react. They don't lose or gain any electrons. Okay, so let's go on to naming your anions. So I'm just going to erase this little bit of information down here so that I have a little more room. And we'll squeak it in right here. Names for anions. A little bit more difficult than your cations, okay? So with an anion, you're going to take the stem of the element name and combine it with the IDE ending, okay? So some of the more common anions that you're probably going to be working with in an introductory chemistry class, we're going to go ahead and write their names out here. They're going to include all of your first 4 halogens. So fluorine, when it becomes an anion, you're going to have the stem, fluor, but you're going to change the ending from fluorine to fluoride. Okay, so here's the stem. I'll underline the stem. Chlorine, when it gains an electron, it becomes chloride. Okay, so your stem is the chlor. Bromine, when it gains its 1 electron, it becomes a bromide. And iodine, when it gains its 1 electron and fills up its valence shell, becomes iodide. Okay, so I'll underline the stem. A few more that you're probably going to run into in your introductory chemistry class. Let's go ahead and write sulfur. So when sulfur gains 2 electrons, because it's a group 6 nonmetal, it becomes a sulfide. Sulfur becomes sulfide. And let's write down oxygen. Also a group 6 nonmetal, so it's going to gain 2 electrons to fill up its valence shell and achieve octet, and it becomes oxide. Not oxygen, but oxide. So I underline the stems there. Okay, so let's go ahead and erase all this and go on to ionic compounds. Okay, and if you're following along in the notes, I'm on slide 4 now. Okay, chemical formulas for ionic compounds. Okay, ionic compounds form when metals transfer their valence electrons to nonmetals. Let's write that here. Form when metals transfer their electrons, I'll just write E for electrons, to nonmetals. Okay. And this forms cations and anions, which have opposite charges. Cations are positively charged, anions are negatively charged, and these oppositely charged particles attract very strongly in a force of attraction called the electrostatic force of attraction. I'm going to write here attract strongly via electrostatic forces of attraction. And these attractive forces are so strong that your ionic compounds are going to be crystalline solids at normal room temperature and atmospheric pressure, and they're going to have very high melting and boiling points. Okay, I'm not going to write that here, I'll just verbalize that. All right, so let's take a look at a visual here. I like doing things that are kind of visual because that's really how I learn. We're all a little bit different. So let's take a sodium atom and a chlorine atom. Okay, so we can look at the periodic table and we can write out their electron configurations. I know this was from tutorial number 4, so I don't want to focus too much on this. I'm just going to really quickly write the electron configuration for sodium. Okay, it's a 1s2, 2s2, 2p6, 3s1. Okay, so 1 valence electron in the outermost energy level, which is the 3rd energy level. And so therefore we know that sodium is going to want to just lose that 1 valence electron. But I'm going to draw this valence electron in what's called a dot symbol, a Lewis dot symbol. So I'm going to put a little dot here to represent my 1 valence electron. You can put it up here or down here, it doesn't matter. I'm just going to put it off to the right. All right, so let's do the same thing for chlorine. 1s2, so I'm counting all the way down to chlorine here. 2s2, 2p6, 3s2, 3p5. Okay, so now we can really see where those valence electrons are in a chlorine atom, a neutral chlorine atom. 2 in the s and 5 in the p of the outermost energy level, which is a 3rd, for a total of 7 valence electrons. So hopefully that makes it really clear why we'd expect chlorine to want to gain 1 more electron. Fill up that valence shell and achieve 8 octet. Okay, so let's go ahead and draw those 7 in a dot structure. 1, 2, 3, 4, 5, 6, 7. Okay, so when sodium and chlorine react to form an ionic compound, sodium chloride, well, you can probably see already sodium is just really wanting to get rid of 1 valence electron. Chlorine is really wanting to pick up 1 valence electron, so it works out perfectly. Let's write this in a different color. For sodium to just transfer its 1 valence electron to chlorine, the result is, take that down, a sodium cation. I'll put a little plus here in between them, and a chloride anion. So I'm going to go ahead and draw that it's got that extra electron now and obtained a 1- charge. Okay, so the positively charged cation and negatively charged anions are going to attract and stay together, and the 1 positive and the 1 negative charge are going to balance out to 0. So overall, the ionic compound has an overall neutral charge because it's going to have an equal number of positively charged cations and negatively charged anions. And we're going to write the formula as NaCl for sodium chloride, our ionic compound. Okay, so let's just take a look at what's happened to the electron configuration, because I keep saying they simulate the noble gas. But let's really prove that right here before we move on. So sodium loses this valence electron. All that's left is 1s2, 2s2, 2p6, 2 in the s, 6 in the p of the outermost energy level, which is now the 2nd. That's the same electron configuration as the noble gas that precedes sodium in the periodic table, neon. Okay? So it achieves the stable noble gas electron configuration of neon. Very important. It doesn't become neon. It has not lost any of its protons. Remember, the number of protons is fundamental to the identity of the element. It's just lost an electron. It's simulating or copying the electron configuration of the stable neon. Okay, what happens over here to the chlorine when it becomes a chloride? It gains that electron into that outermost valence shell. So its electron configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6. In other words, its electron configuration copies that of the noble gas that follows it in the periodic table, argon. So simulates or copies the stable noble gas electron configuration of argon. Okay. All right. So sodium cations, chloride anions, each with a more stable electron configuration, making the ionic compound sodium chloride. Last but not least, I want to remind you that the chemical and physical properties of the compound here do not relate to the chemical and physical properties of the elements which make it up. They are completely different. Sodium chloride is its own unique, pure substance with its own unique and distinct chemical and physical properties. Okay, so let's erase all of this. And let's talk about how to name and write formulas for ionic compounds, which is really the focus for today. Okay, so I'm just going to go in order of the notes, and you'll see on slide 4, the first thing we're going to do is learn how to turn a formula for an ionic compound into a name. Okay, so let's say that we have, let's just write down a couple formulas here. The one in the notes is good, and a couple more as well. Let's say we have, let's do an easier one to start with. Let's do lithium, LiCl, and then we'll do 2S, okay, which is the one from the notes. All right, so let's do these two examples. So we've got a formula. We want to know how to name this ionic compound. This is a fairly easy one, okay? We just have to take the name for the cation, which in this case is lithium, and you can look it up in the periodic table, and then take the name for the anion and drop the word ion completely. So you're not going to write lithium ion, you're going to write lithium chloride. Notice the IDE ending. One of the most common mistakes I'll see introductory chemistry students make is calling this lithium chlorine. Not the correct name. This is an anion, not just regular chlorine. It has gained an electron. It gained it from lithium, so it's lithium chloride. All right, next one, just take the element name for the cation. So we've got sodium. And then here we've got sulfur, but it has gained electrons and become an anion, so we're going to call it sulfide. Don't forget the IDE ending there. Again, most common mistake I always see on the first exam in an introductory chemistry class is students forgetting to change the end of those names and calling this lithium chlorine and sodium sulfur, and that is wrong. That's not going to get you any points. Okay. All right. So let's go on to the little bit harder part, which is to take a name and convert it into a formula. So let's erase this. Okay, so converting a name into a formula, that is slide 5 in the notes if you're following along there. Okay, and we'll just do the two examples on slide 5. So we'll do lithium fluoride and magnesium bromide. Okay, so when you're converting a name into a formula, it's a little bit more complicated. You're going to have to take a look at the cation and figure out what its charge is. Do the same thing for the anion. Figure out what its charge is, and then figure out what ratio of cations to anions is needed to balance out that charge to 0. Because remember, overall, the ionic compound has a neutral overall charge because all the cations and anions balance out. Okay, the positive charge and the negative charge will balance out, I should say. All right, so in this case, let's take a look at our periodic table. Put it right over here. Okay, lithium is a group 1A alkali metal. Okay, so lithium is going to have a 1+ charge as a cation. So lithium ion has a 1+ charge. The fluoride anion, fluorine is a halogen, so fluoride is going to have a 1- charge. Okay, so this one's pretty easy to see how they're going to balance out to 0. It's going to just take a 1-to-1 ratio. So we're going to write it as Li and F. You don't need to write the 1s here because it's just assumed. So you don't need to write a 1 between those. All right, a little bit more difficult. Let's do magnesium bromide. Magnesium, it's a little sloppy there, is an alkaline earth metal. Okay, so it has a 2+ charge as a cation. And bromide is from bromine. It's a halogen, so it's going to have a 1- charge. Okay, so not a 1-to-1 ratio here. That won't balance out a 2+ and a 1- charge. It's going to take 2 bromides, each with a 1- charge, to total 2-, and balance out the 2+ charge on 1 magnesium cation. Okay, so write that as 1 magnesium cation to every 2, it's a little subscript here, for every 2 bromide anions. Okay, now I'm going to show you a little trick that's going to save you tons and tons of time on your exams. You don't really have to think through it the way I did here. All you have to do is swap the numbers for the charges. So bring the 1 down here, but of course we don't write the 1, it's just assumed. So 1 magnesium cation, and bring the 2 over here, 2 bromide anions. So that little switcheroo will always work. Just make sure that if it doesn't give you your simplest whole number ratio, that you go ahead and simplify it down. So if it were to give you like a 2-to-4, then you would simplify that to 1-to-2, okay? All right, so there are tons of examples in problem set 5, but I don't want to overwhelm you with examples here because I don't want these tutorials to get too long. So I'm going to go ahead and just do those 2 examples, but do tune in to problem set 5 for lots and lots and lots of examples of writing names and formulas for ionic compounds. Okay, we're going to go ahead and finish off this tutorial with slide 6, naming ionic compounds that contain a polyatomic ion. So first we're going to start out with what is a polyatomic ion. We're going to define that. Okay. Polyatomic ions are groups of atoms that have an overall charge. So I'm going to write here, groups of atoms with an overall charge. Okay, let's take this down. All right, and I have a whole chart of polyatomic ions on slide 7, and you're going to definitely want to pay attention to which polyatomic ions your instructor wants you to memorize. I guarantee they're going to want you to memorize some of those that I have listed in the chart on slide 7. So let's go ahead and zoom into that and take a look at those polyatomic ions right now. Okay, so starting up here with acetate. Acetate is C2H3O2 with a 1- charge. Now it's usually going to be written this way in an introductory chemistry class. When you get to organic chemistry, they'll usually write it out this way, and that's because this method shows the way that the atoms are actually covalently bound together. So probably you don't need to worry about that method for now. Carbonate is CO3 with a 2- charge. Hydrogen carbonate, also known as bicarbonate, is HCO3 with a 1- charge. Hydroxide is OH with a 1- charge. Hydronium is H3O with a 1+ charge. Nitrate is NO3 with a 1- charge. Nitrite, NO2 with a 1- charge. Phosphate is PO4 with a 3- charge. Hydrogen phosphate is HPO4 with a 2- charge. Dihydrogen phosphate is H2PO4 with a 1- charge. Ammonium is NH4 with a 1+ charge. Sulfate is SO4 with a 2- charge. Sulfite is SO3 with a 2- charge. And cyanide is CN with a 1- charge. So really, this is all just memorization. I highly recommend flashcards for this. Write the formula. Don't forget to write the charge as well on one side. And on the other side, write the full name for the polyatomic ion. Take those with you everywhere you go until you have them memorized, at least the ones that your instructor wants you to memorize. That said, there are a couple little tricks I can share with you. And let's start with the polyatomic ions that share the same stem. So that would be nitrite and nitrate. They share the same stem. And then sulfite and sulfate also share the same stem, the same beginning. Okay, so when you're looking at two polyatomic ions that share the same stem, and one ends in ite and one ends in ate, the ite will always have fewer oxygen than the ate. So for example, nitrite is NO2 with a 1- charge, but nitrate is NO3 with a 1- charge. Sulfite is SO3 with a 2- charge, but sulfate has more oxygen. It's SO4 with a 2- charge. So it doesn't tell you how many oxygen, but the ate ending will always correspond to the polyatomic ion having more oxygen. Okay. All right, another little trick I can share with you is for phosphate versus hydrogen phosphate and dihydrogen phosphate. When I was learning these, I just remembered phosphate was PO4 3-. And then from that, I would derive hydrogen phosphate and dihydrogen phosphate because I remembered that if I added a hydrogen, then I had to take my charge down by 1. So adding a hydrogen for hydrogen phosphate made it HPO4 with 2- charge instead of the 3-. Adding 2 hydrogen for dihydrogen phosphate took my charge down 2. So 2 fewer than 3 is only 1, so it only has a 1- charge. So I'm not sure if that'll help you, but that is something that I used when I was first learning these. So you can do the same thing for carbonate and hydrogen carbonate. Okay, so increasing the hydrogen content by 1, decreasing your charge by 1, so instead of 2-, it's a 1- charge. And then last but not least, might also help you to remember that only 2 of these are cations. The hydronium is a cation and ammonium is a cation. All the others are going to be anions. All right, so hopefully that gets you started with your polyatomic ions. So naming. Going from a formula to a name. For an ionic compound that contains a polyatomic ion. Well, the good news is it's really the same method that you used before we got to polyatomic ions. You're just going to name the cation and name the anion. Okay, so let's do the example in the notes. Got the formula. Looks like this. Okay. All right, so we're going to name the cation. It is a calcium ion. We're going to use the element name, calcium. Remember, don't write the word ion. And then we're going to name the anion. So either you have it memorized or you're using a chart. Probably right now you're still using the chart. This is the phosphate. Okay, where do I have it? Right here. It's the phosphate anion. So PO4 3- is phosphate. And there's your name, calcium phosphate. All right, a little bit more challenging, going the opposite way, going from the name to the formula. But still, we're going to use the same method that you used before we introduced polyatomic ions. All right, name to formula. And we'll just do the example from the notes, which is a magnesium nitrate. So So same rules that we used before we got to polyatomic ions. You just figure out the charge on your cation, you figure out the charge on your anion, you figure out what ratio of cations to anions is needed to balance out the charge to neutral. And then one extra thing you have to do when polyatomic ions are involved. If there's more than one polyatomic ion, make sure you write its whole formula in parentheses and write the subscript for how many of them outside of the parentheses. Okay, so I'll show you what we mean by that. Let's do this problem. Magnesium is a group 2A metal, so it's going to have a 2+ charge as a magnesium ion. Nitrate, either you haven't memorized or you're checking the chart still. It's okay if you are, because you're probably new to this. Nitrate, NO3 with a 1- charge. Okay, so we can use that little switch rule here. It's going to take 2 nitrates to balance out the charge on 1 magnesium cation. Okay, so we're going to need a parenthesis here, because if we just wrote it like this, wrote a 2 there, it would look like we had 32 oxygens and 1 nitrogen, right? And that is not the formula for nitrate, so that would be very misleading. So make sure you use for your parenthesis here. Nitrate, you're trying to say that there are 2 of this whole unit here, 2 nitrates. So 2 goes outside of the parentheses to specify that. Okay, so there's the formula for magnesium nitrate. And that's what we mean by writing the subscript for the number of polyatomic ions outside of a parentheses if there's more than one of them. Okay, so that concludes our tutorial number 5. Do please consider tuning in to Problem Set 5. Well, I will work tons and tons of problems for naming and writing formulas for ionic compounds. Thank you very much.